objective 4, which is to describe the propagation of the action potential from the axon hillock down to the axon terminal, and then talk about how this differs in myelinated versus unmyelinated axons or neurons, okay? And so when you think about this nerve impulse, so we've been speaking about the action potential in a very sort of focused or zoomed in way. We've been talking about it happening in one specific spot as we talk about the events and the channels that are opening and closing. But if we kind of step back and zoom out and think about the action potential as this conduction of an impulse along the length of the axon, we can think about it being passed on from segment to segment to segment along the length of that axon, okay? And in doing so, all that's happening is we are depolarizing different spots of that axon and propagating this electrical impulse down from the soma all the way to the axon terminal, okay? And so what we basically do is we depolarize the neuron, like I said, one spot at a time. And this is also why that is happening in one direction, because of those refractory periods that we just spoke about. So when I depolarize this initial segment of my neuron, my axon, this segment is going to be at rest, right, in yellow. And then after this action potential, right, thinking about the second panel here, this previous spot on the axon is now in its refractory period. It's partly being repolarized as we still have the movement of potassium. And this second spot on the axon is now being depolarized. So it's going to be having or experiencing an action potential. And then this distal part is going to be in rest. And then we're going to see that propagating down again. So this third panel, we see the initial segment now back in its resting phase, so that -70 resting membrane potential. The middle phase, which has just been depolarized, is now being repolarized, and this is experiencing that absolute refractory period. So we could not fire another action potential here, even if we tried, okay? And then the most distal segment of the axon here is now being depolarized. And so we spoke about this phenomenon that the action potential is regenerative. And so as I depolarize this segment, for example, here in blue in the second panel, I am going to create the environment which could potentially expose the neighboring segments to that positive influx of sodium. But because of the refractory period, I cannot depolarize this proximal segment. I can only depolarize the distal segment. And so the action potential can only travel in one direction, okay? And that's again, reiterating this idea that these refractory periods, especially the absolute period, is what keeps the action potential moving in one direction and prevent it from moving backwards. Okay. What we'll speak about now is how this is conducted in an unmyelinated neuron. So an unmyelinated neuron means that there's no external covering to this neuron. And so the way that action potentials are propagated down unmyelinated neurons is very, very slow. The action potential has to go to each individual segment, depolarize every single spot on its way down the axon, okay? From the axon hillock all the way down to the axon terminal. Now, bearing in mind the amplitude of each of these sections will be the same, and it's going to be conducted with the same velocity, the same amplitude, but it is going to be happening very slow because it's going to have to depolarize every single spot, every single segment, okay? And so let's kind of walk ourselves through how that takes place. So here's our axon, right? We've got our soma here proximally, we've got our axon terminal here distally. And again, this is an example of an unmyelinated axon. I'll speak about what myelination means in a bit, but an unmyelinated axon has no external covering. And so it's got no insulation, so to speak. Okay, it's kind of a naked neuron. And so in order to depolarize this axon, I'm going to start with my resting state. So this is a resting state of this axon hillock. And then if I get a strong enough stimulus that comes in from my soma, it's going to depolarize the initial site, right? Remember, the axon hillock is the area where we determine if we get to threshold. And if we do, we begin depolarizing the initial site along that axon. So this is site A. So we depolarize site A. In other words, the inside becomes more negative as sodium rushes in. The inside becomes more positive as sodium rushes in. The outside becomes more negative, okay? Now, as this area is depolarized, we begin to spread this electrical activity. So now it's exposing these sodium channels to that excitation. And again, because of that positive feedback nature, if I begin to expose my neighboring sodium channels to that excitatory state, I'm simply going to move the action potential from site A to site B, okay? And so that's what happens. The action potential spreads from site A to site B. Now, again, thinking about that positive feedback idea, if site B is now depolarized because sodium channels are open, sodium rushes in, I could potentially influence the previous sodium channels because they are in such close proximity to site B. I could try to influence them to depolarize once again, but because of that absolute refractory period, I cannot, okay? I cannot. And so irregardless of the proximity here, the action potential will only spread from site B to site C, okay, because of this refractory period. And so it goes from site B that's now being depolarized, site C is now depolarized, and then site B is in its refractory period. And again, this is what keeps our action potential moving from the proximal part of the neuron to the distal part and not in the backward direction. Oops. All right. Let's speak about what happens in a myelinated neuron. Now, myelination is basically providing some insulation, which helps to speed up the conduction velocity. And this is also true if you think about electrical wires. Insulating them actually speeds up the conduction of that electrical impulse inside the wire. And what happens in terms of our neurons is they lay down these myelin sheaths, and we'll talk about the cells and the process of producing myelin in our next chapter, in chapter 9. But essentially the myelin is this fat insulation. It's actually made of fat that wraps around different segments of the neuron. And what it does is it creates this ability for the action potential to jump or to leap over these sites of insulation, okay? And so the gaps in between this myelination where there are no, where there's no myelin sheath, this is called the node of Ranvier. And the node of Ranvier happens every 1 to 2 millimeters. And essentially this is a naked area of the neuron where there's no myelination, but it has a concentration of voltage-gated sodium channels that would allow for the action potential to happen at that spot, that naked spot, so to speak, and then it can leap over the insulated bit all the way to the next node of Ranvier, okay? And so this type of propagation is called saltatory conduction. So the action potential is pretty much leaping over these myelinated spots, and this is what allows it to speed up its conduction velocity, okay? And so it's not going from spot to spot to spot to spot the way that we saw in unmyelinated neurons. Instead, it's leaping from one node of Ranvier to another node of Ranvier, and it will be conducted or propagated down the entire length of the axon much more quickly in this saltatory fashion. All right, and one sort of interesting example I like to give is if you think about trains, if you've been in a large city with express trains and local trains, it's kind of the same idea. We've got express trains that basically skip several local stops. And so the train can get you, like I used to live in New York City, you can go from Bronx to Manhattan to Brooklyn in 20 minutes, but if you were on the local train, you'd take 2 hours, right? So that's that saltatory kind of leaping from spot to spot and really speeding up the conduction velocity, alrighty? Okay, and here's just an illustration of that further. So we've got these areas that are covered with this myelin sheath, these naked areas, which are the gaps that are exposed. These are called the nodes of Ranvier. These do not have myelin, but they do have a concentration of our voltage-gated sodium channels. And so the action potential leaps from spot to spot, moving very quickly down the length of the axon. All right. And on this final slide here, we're basically looking at how the conduction speeds can differ depending on the amount and type of myelination, okay? So again, the act of myelination is to speed up the conductance or the propagation of the action potential, as well as to reduce the resistance to losing that electrical activity, right? It's creating insulation, which helps to keep that electrical activity flowing in this one area. And so myelination does this. So for example, in our very thin unmyelinated neurons, we would see a conduction velocity of about 1 meter per second. Whereas in our very thick myelinated neurons, we would see a much faster rate, so a conduction velocity of about 100 meters per second, okay? And just looking at this table here to kind of really apply this, our smallest neurons, right, have a really small, or excuse me, our smallest neurons down here with a really small diameter, 0.3 to 1.3 micrometers, have a very slow velocity. Excuse me, they're usually unmyelinated. Think about neurons in our autonomic nervous system. These are neurons going to our smooth muscle, going to the heart, going to glandular tissue. And so these are not going to be areas of the body where we need immediate or fast conduction of impulses, okay? On the other hand, comparing that to areas like our sensory systems, right? Muscle position, muscle movement, our somatic motor fibers. A really good example is the sciatic nerve, right? It's a really long, really thick, really heavily myelinated nerve. And it's in a region of the body where we do need that fast, responsive conduction velocity, because this is actually muscle position, muscle movement. This is actually our sensory perception to things like hot and cold. So if you are exposed to something that can burn you, you're going to move your hand away really quickly. And so the velocity of these neurons need to be much more responsive, much more quicker than some of our autonomic neurons that are not in areas of the body that need to be as responsive. All right. So the whole purpose of this chart is really to show the distinction between our thicker myelinated neurons with faster conduction velocities in areas of the body where that's needed, versus our thinner unmyelinated neurons in other areas of the nervous system where that is not